This is lecture 1.2 of Math 108, Conditionals and Biconditionals. In this video, we will learn about conditional sentences and their associated statements. Let P and Q represent unknown propositions. A conditional sentence is a proposition of the form if P then Q. The sentence if P then Q is false exactly when P is false and Q is true. It is true for all other cases. A biconditional sentence is a proposition of the form P if and only if Q. The sentence P if and only if Q is true exactly when the conditional sentences if P then Q and if Q then P are both true. It is false for all other cases. In the sentence if P then Q, the proposition P is called the sufficient condition or antecedent. Q is called the necessary condition or consequent. By its definition, if P then Q is false exactly when P is true and Q is false. This is because we can think of the statement if P then Q as the rule if P holds then Q must also hold, which is true whenever the rule is followed and false whenever the rule is violated. Clearly, the rule is violated when P is true but Q is false. When P is true and at the same time Q is also true, the rule is followed. So the statement if P then Q is true. When P is false, it does not matter whether Q is true or false. In these cases, the rule is not violated, hence it is always followed. This is because the rule only describes what should happen in the case where P is true, and does not require any specific outcome for the case when P is false. So the statement if P then Q is true whenever P is false. This is the truth table of the conditional if P then Q. Note that the truth value of a conditional statement is independent of any cause and effect relationship between the sufficient condition and the necessary condition. Instead, its truth value depends only on the combination of truth values of the sufficient condition and the necessary condition, as described by its truth table. There are several alternative ways of reading the sentence if P then Q. The most common are P only if Q, P implies Q, P is sufficient for Q, Q if P, Q whenever P, Q is necessary for P. Remember that in the first three statements, the first condition P is the antecedent and the second condition Q is the consequent, whereas in the last three statements, the first condition Q is the consequent and the second condition P is the antecedent. In this set of examples, we are to identify the sufficient condition and the necessary condition in each sentence and give the truth value of the sentence. The sentence, if a triangle has three sides then 1 plus 1 equals 2, is written in if-then form. So the sufficient condition is a triangle has three sides, and the necessary condition is 1 plus 1 equals 2. Since both conditions are true, the conditional sentence is true. In the sentence 0 divided by 0 equals 1 only if the cosine of 0 is 1. The two conditions are linked by the phrase only if. Hence, the sufficient condition is 0 divided by 0 equals 1, and the necessary condition is the cosine of 0 equals 1. Since the sufficient condition 0 divided by 0 equals 1 is false, the conditional sentence is true. In the sentence 17 squared equals 249 whenever 3 pi is greater than 10, the two conditions are linked by the word whenever. Hence, the sufficient condition is 3 pi is greater than 10, and the necessary condition is 17 squared equals 249. Since the sufficient condition 3 pi is greater than 10 is false, the conditional sentence is true. In the sentence, the condition that tangent of pi over 3 is greater than 1 implies that 39 is prime. The two conditions are linked by the word implies. Hence, the sufficient condition is the tangent of pi over 3 is greater than 1, and the necessary condition is 39 is prime. Since it is true that the tangent of pi over 3 is greater than 1, but 39 is not prime, the conditional statement is false. There are three special conditional sentences that are associated with a given conditional sentence. The converse of the sentence if P then Q is the sentence if Q then P. The contrapositive of the sentence if P then Q is the sentence if not Q then not P. The inverse of the sentence if P then Q is the sentence if not P then not Q. That is, the inverse is the converse of the contrapositive. Remember that the sentence if P then Q is not the same as if Q then P. That is, the roles of the sufficient condition and the necessary condition in a conditional sentence are not interchangeable. For example, let us take P to be the proposition 0 divided by 0 equals 1, and Q to be the proposition 1 plus 1 equals 2. Since P is false, the proposition if P then Q is true. Since Q is true and P is false, the proposition if Q then P is false. This demonstrates that the statements if 0 divided by 0 equals 1, then 1 plus 1 equals 2, and if 1 plus 1 equals 2, then 0 divided by 0 equals 1, have different meanings. The biconditional sentence P if and only if Q is true exactly when the conditionals if P then Q and if Q then P are both true. As we just learned, the conditional if P then Q is false exactly when P is true and Q is false, and is true in all other cases, while the conditional if Q then P is false exactly when Q is true and P is false, and is true in all other cases. So the biconditional P if and only if Q is true exactly when either both P and Q are true or both P and Q are false. That is, the biconditional is true exactly when P and Q have the same truth value. The biconditional is false exactly when P and Q have different truth values. Some common alternative ways of saying P if and only if Q are: P is equivalent to Q, P exactly when Q, P is necessary and sufficient for Q. Note the use of the phrase exactly when, which is also what we have been using when stating definitions. This is because all definitions are biconditional statements. Let us give the truth value of the following statements. In the first sentence, the statements a triangle has 3 sides and 1 plus 1 equals 2 are both true. Hence, the biconditional is true. In the second sentence, the statement 0 divided by 0 equals 1 is false, and the cosine of 0 equals 1 is true. Hence, the biconditional is false. In the third sentence, the statements 17 squared equals 249 and 3 pi is greater than 10 are both false. Hence, the biconditional is true. In the last sentence, the statement the tangent of pi over 3 is greater than 1 is true, and the statement 39 is prime is false. Hence, the biconditional is false. You have come to the end of Lecture 1.2. Before you proceed to Lecture 1.3, you are strongly encouraged to answer the exercises included at the end of these slides. Thank you for your attention.